Welcome students and viewers. I am Hussein Yasser from MES College of Arts and Commerce, and we are doing Mathematical Economics 1 ECD 117. This is Unit 1, Basic Concepts in Mathematics, Graphs of Linear and Nonlinear Functions, and this is module number 6. In the outline, we have an introduction to graphs, graphing simple linear functions, and common nonlinear graphs. The learning outcomes are: the students will be able to familiarize themselves with graphical representation of simple linear functions. They would also be able to differentiate between linear and nonlinear graphs. In the introduction, let's first understand what graphs of functions are, and hence we need to know what graphs are and what functions are. A graph is a diagrammatic representation of the relationship between two variables, and a function is defined as a relationship between two or more variables where a unique value of one variable is determined given the value of the other variable or variables. So, what are linear and nonlinear functions then? Linear functions are functions that exhibit a constant rate of change. Hold that thought. I know what you're thinking. What does rate of change mean? We'll come to that in a bit when we look at the actual diagrams. But as of now, let's understand that linear functions are functions that exhibit a constant rate of change, and when graphed, they form a straight line. Whereas, when you look at a nonlinear function, these are functions that exhibit a varying rate of change, and when graphed, they do not form a straight line. Let's look at graphing a linear function. The demand example is the most common example that you and I are so familiar with. So, let's take the demand function. If you look at this function that's on the screen right now, QD is equal to function of P, what it's basically telling you is the quantity demanded is a function of price. Hence, you have two variables here. One is the quantity demanded and the other is the price variable. Now, this is a very general form. Let's take a more specific form, and before understanding what that specific form is, let us see what it looks like. In this case, we have an equation which is QD is equal to 60 minus 10 times P. This is a specific form of a demand equation. What it's telling you is that there is an equation in which the quantity demanded is being defined by an intercept 60 and a slope of negative 10, and the independent variable is price. So, let's find how we can actually plot this demand curve on a particular graph. So, we take the actual demand equation that we have, and let's have a small table here. We'll come to what that table actually means in a bit. So, let's assume that we have some values given for each variable. In this case, we are looking at the price variable, and the price variable we assume has 5 different values, that's 5, 4, 3, 2 and 1, and we are trying to find what quantity demanded values will be filled in here. So, it's a simple way of doing this. Let's look at what we do. We take the same equation, and what we do is we replace the price with the first value 1, right? And once you've done that in this equation, you find that it solves out to get a quantity of 50. So, let's put that in the table there. That's 50 gone in there. In the second case, we are now substituting the value 2, which gives us a value 40. And just like that, we keep filling this table in, and we have our demand schedule, right? So, this particular table that we have here, which shows us the quantity demanded and the price in 2 different columns, is called the demand schedule. And we see that it is indeed a demand curve because there is an inverse relationship between the quantity demanded and the price. You see, as the quantity demanded is rising, it only happens when the price is falling. And as we go on, let's plot this graph now. So, what do? First of all, we need a blank graph. And you look at this graph and you say there are 2 axes. Now, obviously, all of you must be knowing that in a graph there is actually 4 quadrants. But in this case, we have only the first quadrant, because many of the economic concepts that we deals with only the positive quadrants, like for example, quantity of goods or price of goods for that matter. These things cannot be negative. Hence, this particular graph is looking only at the first quadrant, that is the positive y-axis and the positive x-axis. On the x-axis, we've measured quantity demanded, and on the y-axis, we're measuring the price of some good x. So let's see what it looks like. Our first point that we had was 50, 1. That's 50, 1 there. If you see clearly, that's 50 here on the x-axis, and that's 1 there on the y-axis. That's the first point. That's right here. So let's go back. So our first point is 50, 1. Then we have 40, 2, followed by 30, 3, and then we have 20, 4, and finally the last point, which is 10, 5. All is left to do now is plot these particular points and draw the straight line just like that. And there you have it, a straight demand curve, which is nothing but a linear function. So let's understand a little bit more in depth what this essentially tells us. If you see, these are the points that we plotted on that from that demand schedule, right? Now you see these red lines that have been highlighted on your screen. What I am about to show you is that very first question that we looked at, that's the rate of change. So you are all curious about knowing what this rate of change is, right? So let's look at this. So let's say we had to move from this point A to this point B. What it essentially means is that in order to move from point A to point B, I need to give up some amount of this particular price that is there. That means the price has to fall by 1 unit, and when this price falls by 1 unit, you see that the quantity demanded has risen by 10 units. And this very example here, this particular triangle here, shows you that rate of change. In other words, when we go further into the next unit, we are going to depict this by something called by dy by dx, and we'll be doing calculus, and we'll be dealing with in more detail about what this slope essentially means. A very important concept, allowing you to understand what this rate of change basically is. Now, another thing that we need to look at is, if we do this exercise and I take this very same triangle and place it at another spot, I find the exact same thing. Hence, the first argument that linear functions have a constant rate of change. So anywhere throughout the line, the slope will be the same. In this case, it is -10. Let's move on. Let's look at some common nonlinear functions now. So we've seen a linear graph. Let's look at some common nonlinear functions. A polynomial function, right? Under polynomial function, we can have a quadratic equation, that is to the degree 2. We can have a cubic function, that is to the degree 3. And if we look at more specific cases, something that we have seen very often are specific cases where x raised to n. So if you have a quadratic case, then you have x raised to 2, that's x squared. Or if you have a cubic case, you have x cube. And these particular cases are very easy to graph, and we are going to see that in a bit now. Then we have logarithmic functions. We also have exponential functions. A quick note for you, what that degree over there means. The highest power of a variable in a function is called the degree. So if I had an equation in which the highest power for the x variable was 2, then we say it's a quadratic equation to the degree 2. If it's a cubic function, we have x to the power 3, then we say that is a cubic function to the degree 3. Okay? Now let's look at those graphs now. Let's take those first two cases. This is the first case where we have y is equal to x square, and you see the curve almost looks like a U shaped, right? And if you notice that this curve, the half on the right side is pretty much symmetric to the half on the left side. And this is a very special case of a quadratic function in which y is equal to x square. This is a quadratic equation. Now let's look at the cubic one. This is y is equal to x cube, and you look at this particular curve and you know it is a cubic function. So these are the first two that we discussed, a quadratic and a cubic function. Let's move on now to something a little more tough. Let's look at the logarithmic function, that is y is equal to log of x to the base a. This is your logarithmic function, and that's how it looks. And this logarithmic function is nothing but an inverse of another function that's called y is equal to a raised to x, which is nothing but your exponential function. So if you look at these two graphs, they look like mirror images. That's because these are inverse functions, exponential functions and logarithmic functions. Of course, we will have to consider that the value of x here has to be greater than 1, right. So, I hope guys you will have got an understanding of linear function, what linear functions are, and you have seen some of these common non-linear functions on your screen, and these are some reference books for you to dwell upon and get and gain some extra knowledge here. I am Hussain Yasir. Thank you very much. I will see you in the next module.